Here's a nice fact that not many of you might know. If you multiply an apple by 3 apples, it's the same as multiplying 3 apples by 1 apple, okay?
朋友是一个坚韧不拔的纪录片。
Papa Flammy's Advent Calendar.
Here.
Good morning, fellow mathematicians. Welcome back to Papa Flammy's Advent Calendar. We are going to talk about something that probably not many people have thought about before, okay? It's a little number theory thing, has to do with digits. It's pretty cool. You can show it to your family and they go like, what? Bruh. Now, let us take a look at a product of two numbers, okay? For example, 3 times 66. Have you ever noticed that this thing is exactly equal to 33 times 6? Or have you ever noticed that, for example, 666 times 22 is the same as 222 times 66? Okay, for some weird reason, they are changing simply the number of digits, okay? Whereas the digits stay the same. The digit in itself, so 2 stays 2, okay? But the number of digits goes from 2 to 3. It might seem trivial at first sight, but just because it is extremely trivial. Okay, here's a nice fact that not many of you might know. If you multiply an apple by 3 apples, it's the same as multiplying 3 apples by 1 apple, okay? Multiplication commutes, but we want to do this in a more rigorous way, okay? We want to show that this is indeed true. At first, here's the idea. What you might notice is that this thing right here is exactly 3 times 11 times 6. Meaning, this is exactly equal to 3 times 11 times 6. Okay, 3 times 11 times 6. Okay, we are grouping this, and then we are going to get this on the other side out. Now, I would like to make this one step more rigorous, this whole thing. What is 11 exactly? Well, this is 3 times 1 plus 10 times 6. Meaning, if we were to have a 2-digit number at first, for example the 66 right here, we are going to get the first 1 digit, you could say, plus the 10th digit. And then we are going to multiply stuff together. It works similarly here, okay? It's completely analogous. We are going to have 6 times 1 plus 10 plus 11. 100 plus, no, 100. Oh goodness, I'm terribly sorry. This is going to give us 111. My thought process, okay? It's a bit weird. And this thing right here is nothing other than 2 times 1 plus 10, yet again, and so on. And now you can actually interchange stuff, okay? To result in this thing right here. Now let us make this whole process rigorous. Really rigorous, okay? For any number of digits that we have right here. Let us consider at first some number a, okay? Our number a is going to be the concatenation of the same digits, meaning it's a digit d in concatenation with n digits d, okay? Meaning it's, for example, 3, glued together with 3, glued together with 3, and so on, okay? 33, for example. But we can go one stage further. This thing right here is nothing other than, okay, how can we take a look at that? Well, this is just a tuple, you could say, of same digits. For example, those are the digits of a in the first place, comma. The digits of a, the same digit, in the second place, comma. Up until the nth digit of a in the nth place. Okay, we are going to denote it like this. We can make this even nicer. Okay, this is just for simplification purposes later in the game. This right here is nothing other than the digit of a in the ith place. From I ranging from 0 to n. And this is for an n plus 1 digit number, okay? If we have from 0 to n, okay, it's going to give us n plus 1 digits. Just to make sure that we are on the same track. Okay, this does look quite weird, okay? I'm just going to put this here because you are going to see at a glance later when taking a look at the index that stuff has actually changed. Now we are going to put it into this notation that we had right here. If we were to have this, okay? This constellation of 1 plus 10 plus 100 plus 1000, etc. We can actually write this as the sum of powers of 10 times our main digit that we have of the number a. So this is the digit of a times the sum of 10 to the i-th power. Okay, I and I hope you can see where this comes from. From I being equal to 0 to our n. Those two are equivalent, okay, just a different notation. I don't know if this is a common notation, I simply came up with it. And we can do the same thing for number b, okay? B is thus equal to, okay, at first we are going to have the digit of b into jth place, for example, from j being equal to 0 to n. But this m in this case, okay, it can be a different, for example, we had 3 digits here and 2 there. And this is also the sum from j being equal to 0 to m times the digit in b of 10 to the jth power. And now we can take a look at a times b. A times b. And now here's the rigorousness process, okay? We are going to make this nice and formal. This is on the one hand dA in the i-th place, I being equal to 0 to n, times the digit of b in the jth place, from j being equal to 0 to m. But on the other hand, it's just those two sums multiplied together, leaving us with dA sum ranging from I being equal to 0 to n, 10 to the i-th power, and also times, okay, I'm going to put this into parentheses, dB, and then our summation that we have right here from j being equal to 0 to m, and then 10 to the jth power. And well, here we basically go. Now we are just going to use the abelian property of real numbers or integers in this case, dB to the front and dA to the back, leaving us with dB, this time running over the I index, I being equal to 0 to n, up until n, okay, 10 to the i-th power. This is our new number, our new digit thingy, and then times dA from j being equal to 0 to m, 10 to the jth power. Meaning overall, if you put this into this notation, this is why I made this notation up, just because the end result is nice and nice, okay, it's nice and nice. This is dB, this time running over the index I being equal to 0 to n, times dA over the index j, from j being equal to 0 to m. I hope this does make sense to you, okay? And once again, this is for an n plus 1 digit number, and this is for an m plus 1 digit number, okay? And yeah, this is basically it. Now we have formalized this process. I hope you did enjoy this video. This holds for all those palindrome numbers, for those rep digits that we have right here, okay? Yeah, and there's nothing other to say. Hope you did enjoy this video. If you like this video, please like and subscribe, recommend channel if you like, and if you want to support channel a bit more, buy those tiers I create. Don't forget 10 to 15% off everything over the whole course of December. And up until next video, have a flammable day. See ya, ciao.